We're continuing with 8.8 notes for improper integrals with example 5 here. Determine if the following converge or diverge. If they converge, find the value to which they converge. Some of these rules may be helpful. Convergent plus convergent will always equal convergent. If I have a divergent portion plus another divergent, then that will always give me a divergent result. If I have a divergent portion plus a convergent, then it'll always be divergent. If it's divergent minus divergent, then we have a couple of options. So that would mean indeterminate, and we'll have to go do a little bit more work to figure out how to find the appropriate result. So for part A, we have the indefinite integral from 1 to infinity of 2 plus x over x squared. If I can split this up into individual fractions, this may help a bit. So I'm going to rewrite it as 2 over x squared plus 1 over x. If I bring the x squared up top, I have two separate terms that I can find the indefinite integral for. So 2x to negative 2, I go through power rule, becomes 2x to negative 1 over negative 1. 1 over x is natural log of x. I'm going to represent infinity in this expression, limit as b approaches infinity, and then we'll let the upper bound represent the infinity portion with b. So we plug a b into the antiderivative, we get negative 2 over b plus natural log of b, minus, now we plug in the lower bound in, negative 2 plus natural log of 1, so 1 gets plugged in for each of the x's. So we get 0 plus infinity plus 2 plus 0, infinity, which is divergent, plus convergent, will always still result in still divergent, so infinity. Okay, part B, we have integral, indefinite integral, improper integral from 1 to infinity of 1 over x minus 3x over 1 plus 5x squared. The first term, we can use natural log rule. The second term, we can use substitution. We let the u value be the denominator, 1 plus 5x squared. We find the derivative, which is 10x. Solve for dx, we get du over 10x, and then we make our substitutions, and we get integral of 1 over u, which is which gives us 3 over 10 natural log of 1 plus 5x squared. Now we can plug in our upper and lower bound. Upper bound is represented by b, which will hold the infinity as limit of b approaches infinity, and then plug in the 1. So when we plug in b, we get natural log of b minus 3/10 of 1 plus 5x squared, 5b squared, and we know that this we get infinity minus infinity, which means that we have to go a little bit further. So what if we rewrote this as one log expression using quotient property? So if we bring the 3/10 up as exponent, then we can think of this as natural log of a minus natural log of b, which we can rewrite it as natural log of a over b. Okay. So now if we write it in this form, then it's a little bit easier to evaluate the limit as b approaches infinity. If we plug infinity in for the x's, we see that this will still go to infinity, and so we know that the limit as b approaches infinity for this expression, since the numerator will still hold the higher exponent, since the denominator is going to be really degree of x to the 4/5 or 3/5, which is less than 1. So we know that this expression will still go to infinity. So therefore, this sum will be divergent sum. Okay, sometimes the integral can be doubly improper. Okay, so if the improper integral from negative infinity to c and the c from infinity are both convergent, then we know that negative infinity to infinity is equal to negative infinity to c plus c to infinity. So sometimes if we have both bounds being infinity, we can find an appropriate constant, and then we can then find the integral of both separately. Symmetry can also be used to circumvent the doubleness of the propriety. Note as well that this requires both the integrals to be convergent in order for this integral to also be convergent. If either of the two integrals is divergent, then so is the total, then so is this integral in general. So sometimes if we see negative to positive infinity, we need to split into two integrals and choose a convenient internal bound value. So example 6, we have negative to positive infinity, dx over 1 plus x squared. Looks like a convenient, a lot of times the convenient interval is at 0. So if we check out 0 here, negative to infinity to 0 for the first expression, we split this up into two separate integrals here, from negative infinity and then from 0 to infinity. And we're going to treat each separately. The rule for 1 over dx over 1 plus x squared is actually going to be an arctangent rule. So arctangent of x from negative infinity to 0, and then so 0 being the upper bound and b representing negative infinity. And then dx over 1 plus x squared, same thing, b representing the top bound and representing infinity, and then 0 as the bottom lower bound. Okay, so if we plug negative infinity in for this, 0 in for this x here, arctangent of 0 minus arctangent of b, plus arctangent of b minus arctangent of 0. Okay, we know that as b approaches negative infinity, we know this is what our tangent graph looks like. As we approach negative infinity, this graph will level off at negative pi over 2. So we can replace arctangent of b with negative pi over 2. Arctangent of b, as b approaches infinity, we see that the graph is approaching pi over 2, so that's pi over 2. The arctangent of zeros will cancel out. So we have two negatives here, so this is pi over 2 plus pi over 2, which is 2 pi over 2, which is equal to pi. Part B, we have x e to the negative x squared, again from negative to positive infinity, so we want to split this up into two separate integrals, and we're going to let 0 be the convenient internal bound. So negative 1/2 e to x e to negative x squared, and if we go through u substitution, we can let the u value be negative x squared. Our derivative is negative 2x, and so there's going to be a leftover coefficient of negative 1/2. So negative 1/2 e to the negative x squared from b to 0, and then limit from b approaching infinity from 0 to b. If we evaluate the first improper integral here, plug in 0, we get negative 1/2. Plug in b. As b approaches infinity, this will go to 0. Next step up, if we plug in b in for the x squared, we're going to get 0. If we plug in 0, then we'll have remaining of 1/2, and then looks like everything will just cancel out to be 0. Okay, last page here. When an integral is improper, it has a finite interval of integration. Okay, it is improper because it is its interval spans infinite discontinuity. These are harder to spot, so we need to be careful here. Okay, so as you can see, this is from before. Function 1 over x to the p tends to converge to x tends to infinity. As x approaches 0 from the right side at the vertical asymptote. The exception is 1 over x, which diverges in both directions. Okay, when we recognize an infinite discontinuity at an endpoint, we have to set up one-sided limit. When the infinite discontinuity is on the interior, we have to set up two integrals approaching the vertical asymptote from each side of that integral. So in instances, the integral from 0 to 1 of x to the 1/3. It looks like this is going to be a straightforward one where we can just evaluate the integral and plug in 1 and 0. But the problem is that there is an issue at 0. Okay, there's an issue at 0, so we're going to have to we have to treat 0, we'll let b represent the lower bound, and we'll let b approaching 0 from the right side of 0, because we know that this graph cannot exist right at 0 since that's a vertical asymptote. Okay, so there's an improper integral because we have a portion of the graph that is approaching a vertical asymptote. Okay, but we're going to evaluate from here. We're going to go through the same way that we did with previous problems. We're going to find the appropriate integral rule. So if we rewrite this as x to the negative 1/3, we can go through power rule, which is x to the 2/3 over 2/3, plug in upper and lower bound. 1 is the upper bound, followed by the b value. And when we plug in the b, the limit as approaches 0, as b approaches 0 from the right side of 0, this will go to 0, so that leaves us with 3/2. Part B, again, from 0 to 1, there's an issue at 0, since 0 is where vertical asymptote occurs. So we need to let limit as b approaches 0 from the right side of 0. Let's figure out the rule for x to the third in the denominator. If we flip this up to the top, it becomes x to the negative 3. Go through power rule, we get x to the negative 2 over negative 2. Plug in the upper and lower bound. 1 gets plugged in, which gives us negative 1/2. Then we plug in b, which is negative 1 over 2b squared. If we evaluate b 0 from the right side of 0, so if we keep decreasing this value to be 0.1 squared or 0.0001 squared, this value will get smaller and smaller, which will then cause this to be greater and greater, and so this will cause this fraction to go to 0. Since b value is getting smaller and smaller, that will cause this fraction to get larger and larger to infinity, and then we have convergent plus the divergent, which will leave us with still divergent. Okay, example 8, a and b. The integral from 0 to 27 of dx over q root of 27 minus x. This is where we have to be a bit more careful here, because, well, actually this one, the place where the series or this the divergent value is at 27. So again, we're going to have to consider that the upper bound cannot be reached, but we can let b approaching 27 from the left side of 27. Since from the left side of 27 will still cause this to be a value that will be defined. So then, if we bring this denominator up to the top, we can rewrite this as 27 minus x to the negative 1/3. We go through use substitution, and we make our find the integral of u to the negative 1/3, which is u to the 2/3 over 2/3 with a negative 1 that's in front. Plug in the upper and lower bound. Our upper bound is represented by b. So plug b into the antiderivative followed by the 0. Now we can evaluate b as b approaches 27. So approach 27 from the left side. Eventually we'll make that go to 0. And this expression will just give us 3/2. 27 to the 2/3 is the same thing as cube root of 27, which is 3. 3 squared is 9. So 3/2 times 9 will be 27 over 2. All right, part B, the integral, definite integral from 0 to 3 of dx over x minus 1 to the 2/3. Now this looks like something that would just be very straightforward, right? We find the integral of this expression, maybe use substitution and power rule, and then plug in the upper and lower bound. But here's the issue. The issue is at 1. What's happening at 1? Well, at 1 will cause this denominator to go to 0, which will cause this expression to be undefined. So there's an improper value between 0 and 3. 1 is a vertical asymptote, so there's a discontinuity at a point that sits between the endpoints. So these are a little bit harder to catch, but once we see it, we have to rewrite that as two separate integrals, one from 0 to 1 and the other from 1 to 3. Okay, we have to be able to split the integral up on either side of that discontinuity. All right, so if we bring this, let's do the one at a time here. If we bring this x minus 1 to the 2/3 up to the numerator, it becomes x minus 1 to the negative 2/3. Go through use substitution, power rule. We're going to get x minus 1 to the 1/3 over 1/3. And because we apply the integral, the antiderivative, the integral notation drops out. I'm sorry, the integral notation's here. It drops out of this second expression here. Okay. So we still find the integral of x minus 1 to the negative 2/3, which gives us x minus 1 to the 1/3 over 1/3. All right, so the first thing is we're going to evaluate the limit as b approaches 1 from the left side of 1. Okay, so this represents the left side of the vertical asymptote, and this represents the portion that's on the right side of the vertical asymptote. So on the left side of the vertical asymptote, we're only approaching from 0 to 1 from the left side of 1. Okay, so b plugs in, followed by 0, and if we simplify that, plug 1 in for b, we get 0 plus 3. Now for the second portion, the integrand will apply this with the same rule, and we can find the same antiderivative. Plug in upper and lower bound, 3 upper bound, b being the lower bound. This time it's 1 from the right side of 1. But first thing we do algebraically, we always plug in that target x value and see if that gives us a real number. So 1 gets plugged in for b. We get this portion gives us 3 times 2 to the 1/3. This portion gives us 3 times 0, which is 0. So if we combine all these terms, we get 3 plus 3 cube root of 2. And so this is as far as we can go. This is our convergent sum.